Okay, let's do a Mux and Morley experiment example. Before we get to how they were trying to measure the ether, let's just see how the interferometer works and how a modern interferometer works. So again, remember what we have is we have a light source, a single light source that comes to the beam splitter. It follows path 1, it bounces back, bounces off the beam splitter, goes to the screen, and then path 2, I'll do a different color, path 2, and I'll just do a different color when it splits off. So it bounces, it goes up, bounces off the mirror, comes back and goes straight through. So those two beams meet at the screen, and at the screen we get some sort of interference pattern. And we know that the space between the dots, that there's a destructive interference where you don't see light, and constructive interference where you do see light, and you can do some geometry, maybe complicated geometry, to figure out like the spacing between the dots has to do with how much farther apart one beam is from the other. Actually, that's not quite true. It's not complicated because the beam in the dot in the center is from the two. Oh wait, but they may not follow the same path. Okay, so if path 1 is, let's just assume that path 1 is equal to path 2. Now that's going to be impossible to do, but it doesn't matter if it's not the same. But just for the simplicity of calculation, we're going to assume path 1 is equal to path 2. So if the two beams follow the exact same path, then the central dot is going to be when they are off by 0 wavelengths. The first dot to the left and the right is going to be when they're off by 1 wavelength. 2 wavelengths when you're 2 dots away from the left and right, etc. Or if you're looking at the dark spots, right, the middle in between the dots, then they're going to be off by a half wavelength to the left or right, by 1.5 wavelengths, etc. Whoops. Anyway, okay. But that's not actually what's important here, which is also why it doesn't matter if path 1 equals path 2, because how we use the interferometer is not looking at that interference pattern. It is saying, oh, what happens now if we change one of the paths? And then how does the interference pattern shift? How do the dots shift to the left or to the right if we change one of the paths? And again, we said if we, for example, move one of the mirrors farther out. And actually, there's a really interesting experiment called LISA and LIGO, which is the trying to detect, let's see which one's which. Light interferometry. LIGO is Light Interferometry Gravitational Observatory, or something like that. And LIGO has been running since just after I was in grad school, I think, since the mid-90s, and it has recently been successful in detecting gravitational waves. That's why it's called the Gravitational Observatory. How does this work? Is that this is actually an incredibly large laboratory. I believe, let's just say, I think it's maybe the path 1 and path 2 are a couple of miles. And the mirrors are attached to what I drew last time. They're actually attached to these really large, perfectly spherical balls made of some kind of metal, silver, I think, or something like that. But really large, like big. And they're hanging underground, these large balls. And you can look it up. Look up LIGO and you can see how big it is. But I got it. They're like room-sized balls that are a couple miles apart in an observatory, in a Michelson-Morley, in an interferometer that looks like this, but just a much larger scale than Michelson-Morley, which was about 1 meter. Instead, it's miles. And what they're looking for is a shift in the mirror. If one of these mirrors shifts, right? If one of these mirrors, let me find a different color. If one of these that's a bad color. If one of these mirrors shifts left or right or up and down, well, this is, it's going to be east, west, north, south kind of thing. Then what you're going to see is this shift of the interference pattern, because one of the paths, if one of the mirrors shifts, then one of the paths is going to get shorter relative to the other, which will shift the interference pattern. And it turns out that the larger you make this device, the more accurate it is, and they can measure shifts in these mirrors of like the size of a nuclear diameter or something, 10 to the minus 15th meters or something like that. And that can be measured by a shift of an interference pattern in the interferometer. Now, why are they doing this? What they're doing is they're trying to detect gravitational waves. You should, as a physicist, know about the gravitational waves. Gravitational waves are something that were predicted by Einstein's theory of general relativity, but they have never been measured. Why haven't they been measured? Well, two reasons. One, they don't exist, maybe, but actually we're quite certain they do. We're so certain that we're willing to spend billions of dollars on these incredibly sensitive experiments. And the second reason is that gravity is a weak force. Remember, when you talk about the four fundamental forces, gravitation, the weak force, electromagnetic force, and the strong force, gravity is by far the weakest of these forces. So it's really hard to detect gravitational waves. What is a gravitational wave? That should be something that you can actually figure out from the words. If an object has a gravitational field around it, then if you oscillate that object, if you move that object, you should create a wave, a disturbance in that field that travels outwards. But it's such a weak disturbance when you move an object. If I have a mass, if I just take my phone and I wave it in front of me, right, I'm creating gravitational waves. But it's such a weak disturbance in the gravitational field around the mass of the phone. Remember, all masses create their own gravitational fields. Something you should probably remember, that all masses create their own gravitational fields. All masses are gravitationally attracted to all other masses, right? Gravity isn't just for the Earth, it's for all masses. So you create this gravitational field, gravitational wave and a gravitational field. When you take an object and you shake it up and down, you create a wave that propagates in the gravitational field, but it's so weak that we can't measure it. We haven't measured it. And the only time that we think, where we are only sensitive to incredibly large disturbances in the gravitational field. And we can't create a large enough disturbance on Earth to detect. So the only way we can currently detect gravitational waves is to wait for an incredibly large intergalactic, interstellar event, like a star exploding. A star exploding is a much larger event than we have ever experienced on Earth, and hopefully larger than we ever will, although that's not really true. And so when a star explodes, then we think we can detect gravitational waves. So we have to build this device, wait for a star to explode, and then see if we detect it. Now, what is it that we're going to detect? According to Einstein's theory of relativity, and this is the whole weird stuff about Einstein, is that the theory of relativity says that space and time are deformed by gravity. That's general relativity. It's not an apparent deformation, it is a real deformation. Space and time are deformed by gravity. So, imagine a gravitational wave coming in from left to right. So I'm now going to scribble over this picture. A gravitational wave coming in from left to right. What that's going to do is it's going to squish the sphere on the right. It's going to squish that. And I showed it just as two arrows pointing outwards, but it's going to squish it and then expand it in that direction. It's going to squish and expand. Maybe I should do it a different color. Let's do it orange. It's going to squish and expand it like this. It's going to squish and expand this one like this, because the gravitational wave came from left to right. So it will only move the mirror on the right, not the mirror on the top. And if it moves the mirror on the right because it squished that big metal ball, then the diffraction pattern will shift. And you say, well, wait a second. First of all, how do you know it's going to come in left to right? Well, we don't. So you got to watch. Like maybe it comes in top to bottom. Maybe it comes in at an angle and we're unlucky, right? But likelihood is it's going to come in one way or another that's going to be detectable. But in order to hedge our bets, we have two of these labs. We have one of these labs in Louisiana and one of these labs in, I believe it's Colorado somewhere. I believe it's Denver. And what we do is we look for an effect in one lab and then the other lab, because these waves pass all the way through Earth, right? And so those two effects should happen because these waves would also travel at the speed of light, those two effects should happen at the speed of light apart from each other. So you're looking for correlation in effect at two labs that are in two different places. So this gravitational wave would deform these masses, which would move the mirrors, which would shift the pattern. If we can detect the gravitational wave, then we can say, ooh, Einstein's theory of general relativity, which is an incredibly important theory, is correct. Now we have detected gravitational waves. We've not detected many of them, but within the last couple of years, we have finally detected gravitational waves with these experiments. Huge deal. You should go and Google it, read about it. There is in the works a much larger experiment, which would be on spaceships in outer space, separated by much more than miles, that would be much more accurate. That's the LISA experiment, probably on hold for budget reasons, but in any case. Okay, let's come back to the tabletop Michelson-Morley experiment.